All right. So today we have Ashutosh here from Georgia Tech, and he's going to be presenting his recent work on RLHF called Leftover Lunch. So yeah, if you want to give yourself like a brief introduction as well, you may go ahead. Ashutosh, if not, you can just get started.
Sure. Let's share the screen again.
And then if anybody has any questions, just tell me. There's sometimes some echo that comes up in the presentation, so I'm gonna mute the room. Okay. So.
Okay. So hello everyone. I cannot see you guys, but hope you can see me and hear me clearly. I'm Ashutosh. I'm from Georgia Tech, and I'll be presenting my two most recent works on offline RL for large language models. And yeah, let's get started. So I guess I will not go.
You guys can open this if you want.
Very well. So I hope you bear with me.
Yeah, this one's cheap.
My most recent work is advantage-based offline reinforcement learning for language models, and this was accepted in IPLR. So so let's get started with the motivation. There is an abundance of language data and also pre-trained classifiers. We have like internet data, human conversations, crowd collected data, forum data, and there are like many existing classifiers on Hugging Face for various kinds of attributes, toxicity, fluency, sentiment, formality, etc. So the main question here is how do we extract the desired model behavior from the existing data and classifiers? So the classical method is just data filtering and supervised fine tuning. So you filter the data using thresholds on classifier predictions. You further fine tune on this high quality subset, but this requires you to understand your data quality and your classifier's behavior, and then you will have to manually tune the threshold to filter out the data. Another option is RLHF, where you collect a huge amount of human feedback, and then you train a reward model on top of it. Use online language model exploration with this reward model and PPO or any other online method. And this is another method which works well, but the problem here is that you require online exploration from language models, which is which is finicky. If your language model is not good, there's like exponentially large action space, and like many of the times it's like tricky to make this work. So what's like a simple thing we can do with its offline RL? You can basically take language model on existing training data. Like towards your desired task. So I guess I do not need to go over this. This is like just overview of RLHF. Like I said, you need prompts, like an initial language model will generate some text. Humans will rate it. You will get a reward model, and then you like this. Once this reward model is trained, you can again use the prompt data set, initialize your final policy with this initial language model, and collect online trajectories, plug in the reward, update with PPO, and then you get a better policy. However, as I said, this is expensive due to online exploration. And there is also this sparse reward problem where you are like decoding token by token, but your reward comes at the end of the sequence. So it makes it difficult to estimate the value of the intermediate tokens. So to fix both of these problems, the key idea we had is why not use the entire action as entire sequence as a single action, and then plug in advantage. So essentially how we define things is language tasks. All language tasks are basically an RL environment. So your state space can consist of all possible language prompts. And then your LLM agent, it has an entire output as a single action. So your whole sequence is one action. And then you can rearrange the terms and plug in arbitrary reward function in it. You don't have any discount factor since it's only one step. And then this allows you to also compute sequence level value estimate and sequence level advantage. So let's get into the details. So first thing is we start off with this one step of policy gradient. So here we assume that we have a reference policy, which is supervised fine-tuned policy in most cases. You can plug in an arbitrary reward, which we'll come to later how we define that. And then this is your target policy that you want to fine-tune on this arbitrary reward. You can multiply and divide with, like you can reshuffle some terms, and then you can get like a much simpler objective by essentially like now you can sample your X and Y from the training set. You can plug in that arbitrary reward. You have this extra additional importance weight term between your current policy and your reference policy. And then the last term is basically just like negative log line. So overall, like this, sorry. I mean, this is like a much more tractable equation where you can plug in arbitrary reward. And then another trick that we came up with was basically substituting with this reward with the reference policy advantage. So next, I will show you how we calculate it. Actually, yeah, let's go there. So this method we call advantage leftover lunch. I'll tell you why it's called leftover lunch. So overview of the method, we basically have some training data of sequences X and Y. So X is prompts, Y is responses. You first do supervised fine tuning to get your reference policy. This is the standard like supervised fine tuning. In the next step, you will first plug in your external reward. So let's say your, I don't know if my cursor is too good. Sorry, I'm very new to Mac, so I'm not sure. Anyways, so we'll work with what we have. So the first step is you get some external rewards, which can be arbitrarily defined. There is an internal value estimate of the reference policy, which we will compute in the next slide. But essentially, you can estimate the value for every prompt in your training set. And then you subtract these two and just extract the positive advantages, which we call the leftover part of your data set. So the negative advantage, like naturally, like there will be some instances which will have negative advantage, some will have positive advantage. We discard the negative ones because in our applications, we didn't find them to be useful.
Sorry.
Towards the,
just one question.
And
Okay, actually, I have one question. So, like intuition wise, what does the value function over like a prompt X means? Because like in RL, it means it's a cumulative like value, right? But here, like what does it mean to have like a value associated with a prompt under some policy?
so the value here is essentially taking X and the reference policy. This is like trying to guess what is my reference policy gonna obtain if it actually generates some response towards a particular prompt.
So was this reward function generated under the reference policy?
Yeah, so like we'll come to the next slide, like how it's exactly calculated, but the core idea is that this V pi ref X is trying to estimate for your arbitrarily defined reward, what is the expected reward it's gonna get for just this particular prompt without like actually generating the response. So you just put in the prompt and your reference policy and get this, there's like an additional layer on top of this reference policy, which will give you this final score. And you can actually look at your training set, okay, this is the reward that I have in my training data, whereas what is like the difference of that with the value that I compute? Does that make sense?
Yeah.
I have a follow-up question to what I asked. When you're saying, so you're assigning value function to your entire prompt X, correct? So is there correlation between your, so I mean, I'm trying to understand where the temporal structure comes into play here, in the sense that, so X is basically a state, right? I mean, I consider it as a state. So if the prompt at t plus 1, is there some temporal structure between prompt at?
So like I said, this is like one step assumption, right? So there is no temporal component to it. Like we simplified the whole part of like value estimation. Now you only estimate value on your, so like in the classical, like or like the most standard RLHF implementations, you would have like every sub token as an action, or like every token as an action, and then you will have like X comma Y less than I as like that would be your state space, right? Like all the intermediate Y tokens as your state space, you will estimate value at each particular temporal, like at each token value. each token index, but now you would only get one single value for the prompt, and that's it.
So then, so I'm trying to understand what is the difference between the reward you get for a, so difference between say R of X and V of X, or like there's no such thing as R of X.
Yeah, there is no R of X. The R is dependent on X and Y both.
Okay.
Yeah. Any other questions?
So if I just understand correctly,
Yeah.
like the R function, basically reward you get arbitrarily from some data. It could be gold model, it could be anything.
Yeah.
And now you want to estimate the potential reward of a given prompt under some
Mhm.
PyRef policy. So
Yes.
so V is more like a potential reward on the X prompt rather. Like if you
Mhm.
this is like think of it completely in like a bandit setting.
Yep. Yep. Yep.
Okay, maybe it will be clear, it's still in some, but I think it will be clear.
Yeah. In the next slide, when we come to the value estimation prediction, you will like, I guess you'll grasp it a little bit better. But yeah, basically we want to, so in order to not bias this VPyRef too much, we will take like a small validation set. So typically in your like standard training, you will have training validation tests, right? So we will estimate this VPyRef on the rewards that is obtained on the validation set. I guess let's like skip to that slide. So yeah, you initialize your VPyRef as like a attention plus linear. This could be anything. So like some set of layers on top of frozen reference policy, and then you generate a bunch of sequences with your PyRef on the validation set prompts. Then you get the rewards on these like Y primes, and you train your rewards, train your value estimate on these rewards using the mean squared error loss. So this is how you get value estimate for the reference policy. This is like just to highlight, this is like a very crude estimate. And in my like experiments, this value estimate MSE loss never goes to zero because your most of the parameters are frozen. So you're not back propagating through your reference policy, that stays frozen throughout like the subsequent ALOL training. Is this part clear, or do you have any questions on this? Okay, so let's go back to the previous slide. So again, we have this external set of rewards which we'll define arbitrarily. We'll train this value estimate on the validation set. So you basically, I think like in typical training, you run your reference policy through the validation set anyways.
Yeah.
So
Sorry, just one
Can you
question.
go back to this?
yeah.
Yeah, so basically your value function is like, you're fitting the value function based on an MSE loss. if I'm not-
Yes.
And
Yes.
the MSE loss is the reward.
So the reward of X comma Y prime minus the value of reference of X. So that's like the error or like the mean squared error of that difference.
Okay.
So to give you like concrete numbers, like let's say you have like 100,000 training instances and only 1,000 validation instances. You run like the standard validation loop on your reference policy. You will try to get the average reward of reference policy on the validation set. But now for each particular instance in your validation set, so you will take R of X comma Y prime minus V pi ref of X, the whole square. That's the loss you would train. So like,
But we don't have the
Yes.
V pi ref, right?
huh?
But we don't have
What?
the V pi ref.
Can you repeat?
So do we have V pi ref in the data? Like, we don't have V pi ref in the data.
No. V pi ref is the thing that we estimate
Then you're
in our.
bootstrapping.
No, there's no bootstrapping because there is no next state. Yeah, even like
Yeah, it's.
I'm confused because like your target function here is R of XY,
Mhm.
and you want to optimize the V theta, right? You want to find the V theta, and your loss function is R of XY minus V of X.
The
So,
whole square.
but if let's say if you're training it only on the validation data, then you wouldn't have the repeated X prompts, right? Right? Or do you have the repeated X prompts?
Yeah, these prompts will be not in the training set, yes.
No. I mean, like in the validation data, do you have like same prompts but multiple Ys for it? Because
No. So again, this is a very crude estimate. I just take sample once and it doesn't have to be like super robust. I mean, like I want to like do more robust analysis of like how much value estimate matters, but in my experiments, I was like just running this for 10 epochs on like, let's say like 1,000 instances, and you get like a pretty decent value estimate from that. And to like give you more empirical analysis, I tried, so like this is some examples from helpful and harmless conversation, helpful and harmless assistant from Anthropic. And I was looking at the preferred, so they have like prompts, chat history, good and bad responses, like pair of responses. I was only looking at the good responses. And then if you estimate the value on your validation set and then plug in your reward. So this reward is coming externally from like some other like pairwise ranking model. And you will see that the reward here is pretty low for the first conversation, which is like very bad. So this was like a red teaming conversation. The good response here is also super bad. But since your policy is expected to do very well, like your policy is expected to actually generate a safe response for this conversation, and you would subsequently get a very negative advantage for that. So I think like the cool thing about this is like it automatically highlights the bad quality training data using this like value estimate trick. And in general, like I did like a more fine-grained like manual analysis of like the top negative advantage data points, like top 50 of them. Many of them were unsafe and others were not super helpful. So like in the second one, it like expresses an opinion where it should not express an opinion. So like this is like another conversation which you would like try to elicit some bad response from the language model, and even like the good response in your training data is actually quite like not what the ideal behavior should be. But this value estimate is able to capture that.
Still confused about the value function, but maybe
So correct me if I'm wrong, but I believe the value function is calculated by just like doing some sort of, you just sample from the reference policy and then you find like the expected reward for that specific prompt. So you're just building the value function of just like some small like Monte Carlo estimate.
Yeah, yep. That's correct.
Okay.
That's like a good way to think about it, yeah.
it's probably more like, since the data set is very small, so when you learn a value function like on such a small evaluation data set, you would not overfit. So ideally, if the target is R of XY, you're kind of learning true value, right? X comma Y. But when the function is so small and the data is so small, you're kind of learning like the approximate reward that you would get. So by now choosing like a positive advantage, like this is something which is also done in like batch RL, right? Where you have like a noisy data set and you want to probably like find good data set from it. So they're also like, I think positive advantage like work in a sense, because you're saying that, oh, which are the responses which have more potential? So you want to like learn over them. So probably like this is probably working because the network is too small and you're not overfitting. So you're kind of like just estimating some crude reward that you can get from it. Like think of value function more like that.
Yeah, I mean, in all the experiments that I had, this was just like one attention and one, like in the first version, I just had like a linear layer, not even like an attention layer. That was slightly, like at least like the MSE loss, if we look at that, like with attention, you get like a lower MSE, and in general, I saw that the lower MSE you get in this like validation training loop, the better final outcome, like the tested distribution you get. So again, like to not bias our evaluation too much, like your value estimate is only looking at the validation set rewards. It's not even looking at the validation set generations from your reference policy, just the final reward. And then you get like this V by ref. And finally, like you subtract both of them, you get like a scalar value, which is this positive advantage for every instance in your training set. You incorporate this in importance weight term, multiply that with NLL. So effectively, it's like multiplying two scalar terms to your NLL objective. And finally, when you do like just one epoch of training with this positive advantage examples, you get a much better tested distribution with the ALOL's policy. So on the right, I'm like showing you a Boylan plot of the reward distribution for the test set prompts. And like ALOL is typically getting much better. Like this, it should be basically thicker on the top. And we have like in the paper, if you go, you will see like many variations of importance weight that we derive. So even like as like in one of the variations, we like simply set this importance weight equal to 1, which is like a very bad approximation, but even that works. So the key thing is this advantage term is like the main thing that contributes to most of the performance. Importance weight will just give you like a slight boost based on like how you parameterize it. But like this, the key thing was like there was still a lot of leftover lunch, so to speak, in your training set. If you like just rank it with your reward model, get the estimate of like where my language model is already good and where is it bad, and you only train on the regions where it's still bad. Does that make sense?
Yeah. Yeah, all good, I think.
Okay.
Thanks.
So like I said, there is a reference policy. This reference policy, this value estimate would automatically highlight the bad quality data. Another thing that I didn't highlight in the paper, but was also an interesting insight we find was, if you look at the like low value estimates, like where the value estimate is really low, those were the prompts which were usually tricky for language models. So for example, we did this experiment on common sense reasoning task, where essentially you have a situation and you want to predict what is like the behavior that is expected out of this situation, like what this situation entails for person X or person Y. In like, let's say it's like a two-party situation, you would want to ask like, okay, what would happen if like person X hits person Y, something like that. So in that task, we looked at the value estimates which were very low, and it automatically highlighted the prompts that were that had negation in them. So the prompts were something like, what would not happen if person X hits person Y? So those kinds of prompts are like more tricky for the language model because there is many diverse answers that you could come up with, which could be good. So like this value estimate is like kind of like the key thing here, which is making it work. It highlights the regions where the reference policy is uncertain, and it also highlights the regions where the reference policy is very certain to do well. And you can like use that to essentially organically filter your training set and like re-rank it to make it better. So let's move to the next slide.
Sorry,
now
just another.
discuss the sorry.
How is reference policy different from the SFT policy? Like, what's the difference?
It's the same policy. Yeah, the reference policy is SFT.
Okay.
Okay. So next I'll discuss the offline and online RLHF landscape. So here, in the offline aspect, there is like DPO reference free. So you can like just use the preference data, which is basically pairs of win and loss for every prompt. Or and within that, there are like certain methods which use the reference LM and certain which don't. This was like way back, but now there are like many more preference-based methods. And another aspect is to just do policy gradients. So in offline policy gradients, you can just do weighted behavior cloning, or there is like another paper gold from I think Her's lab. And our method falls somewhere around this, where it's like essentially it's able to use advantage, the reference LM, and it doesn't require reference data. So it can use any kind of X to Y mapping that like helps it generalize much more. And then you can also plug in like arbitrary reward functions, which you cannot do with DPO basically. So it's like very close to online, but it's very close to PPO in terms of how it operates, but it gives you the flexibility of using any data set and any reward function that you want. And these like the subsets here, like the subtitles for ALOL are basically the different importance weight sampling I mentioned. Like there are 4 different variations. One is KL, one is reference free, another is like sequence, where essentially for this importance weight, instead of you can actually again disentangle this to per token importance weight while keeping the sequence level advantage weight. So you can think of like a flat advantage weighing for the whole output sequence, whereas the importance weight can still be per token. So this gives like a lot of flexibility to work with. And I guess so now let's talk about the evaluation setup. So in each, like we'll go through 2 tasks. There are like 4 in the paper. But the general framework is like you have training and validation set. You fine tune your supervised with supervised fine tuning for 100% of the steps. You get a reference policy, and then you continue fine tuning with baselines or our method for additional 50% of the steps to get a newer policy. And finally, you evaluate both of these on the test set, which is unseen. So the baseline we use here are supervised fine tuning, weighted behavior cloning, this reward gold, like I said, a modification of gold method which allows sequence level rewards. There is TPO PRO whenever preferences are available, and finally like ALOL variants, like one is with reward and another with different importance weights. So the 4 tasks we tried were helpful and harmless assistant with 7 billion parameter language model. I was using LoRa here, and like here human preference labels were available. In other 3 tasks, we tried something crazy, like so in Reddit response generation, we thought, okay, what do we want a language model to be? What would we want a chatbot to be? Like what were the attributes that we want out of a Reddit chatbot? And that would be fluency, engagement. It should be like generating popular, likely to get upvoted responses, safe, also diverse. Like I said, there was a common sense reasoning, understanding social situations, and then there's also faithful knowledge grounded dialogue, where here you want to improve factuality, diversity, engagement, and fluency. So in basically Reddit and the faithful knowledge grounded task, we had 4 different reward components, you could say. So each of these were basically either a classifier or diversity. Was in the diversity we used a length normalized TF-IDF score, and we tried to ensure that all these reward components would be in the range of 0 to 1. So you could just basically sum them up to come up with one single final reward. Yeah.
Question.
Question.
So assuming these reward models are gold models, like how would you make sure that given a like, so for example, you're measuring on these different reward functions like fluency and diversity, but how would you measure that the response that you're generating is also relevant to the prompt? Because these are measuring like different aspects of the the response.
I mean, so I personally think that you could, if you have like a relevance reward or like a relevance classifier, you could just plug that in, add that as like another reward component, and add it to your reward function.
So what is the part here at this point? The relevance.
In this set of experiments, no, we like I mean, like I didn't per se did like a relevance classifier. I couldn't find it, but like I manually eyeballed the responses. They were looking pretty fluent and actually strangely quietly diverse as well. Since we had like a diversity as like a reward component, they turned out to be much more diverse than the supervised fine tuning policies. So interestingly, like without changing the training data, you do supervised fine tuning and then you add like this kind of external rewards, or take a subset of the training data set and then fine tune further with ALOL, and you get much more diverse and much better model from the same training set. So that was quite impressive.
So was the relevancy like become natural part because you have the X and the Y, like in the data set? So probably they are already coming from a nicer, like a
Yeah.
LLM based model. So that is kind of checking your relevancy part already, like taking care of it.
So if you are assuming that your training set has on an average relevant outputs, so I am guessing like if you use Reddit responses, they will be relevant to the post, right? So you have like post comment pairs, you would like not, like in the actual human conversation, the comments will be relevant to the post. So you're not actually going out of the distribution at all. You're just using the same distribution, like rather a subset of that distribution.
I see. And for all of these, like, did you already had like gold reward models, or you built like your like you
No,
trained the
I
classifier?
actually, like I said, like the main motivation was we have training data and we have a lot of classifiers. So for fluency, for example, we use COLA classifier, like the corpus of linguistic acceptability. Engagement and popularity were dialogue RPT models. These were again pre-trained by Microsoft. For safety, I used one of the models from my previous study, which was ToxiChat. So it's like trying to figure out whether this is offensive or not. And for diversity, I plugged in like a TF-IDF score. So you can basically like throw in any component that you care about. Like let's say, like you said, like relevance. If you can find a relevance classifier, throw that in, or if you want to train it yourself, you can like add that as a separate component as well.
How did you, sorry, just one specific one. How are you measuring engaging and popular for Reddit? I'm guessing maybe the engaging one is a classifier, but for popular, you have to.
So if you look at dialogue RPT, just like search it on Hugging Face, there are two different models. One is up-down, which is
Yeah.
So what they did was I think like a ranking model where if you like have a prompt comment pair with upwards, you would give it like a 1 classification score, and if it's with downward, you would get a 0 classification score. You just train a ranking model on that.
Right.
So that would give you like a probability of getting upvoted. And for engagement, they said, I think is there like a follow-up comment or not? So that's like another classifier signal that you can get to get like engagement basically.
I see. And are these, because I'm guessing a lot of these are user dependent, like do they have like specific user information for this or no? If you know.
Sorry, can you?
Like a lot of these reward or like engagement would be user dependent from Reddit. Like I wonder if you know like if they have like any user information about
I think it was generally trained on all
just generic. Okay.
But I mean, yeah, I mean this framework doesn't stop you from adding any user specific thing as well. So that's why like I added a star in this. In general, your reward function can add more components to it outside of just X and Y. If you have like some metadata you want to add, you can plug that in.
Yeah, of course. Yeah, it's just an arbitrary reward function, you're right.
Yeah. Okay, so these were the tasks. Okay, let's go with the helpful and harmless assistant task. There is like a lot going on here, but we want to like highlight 3 things. So we had like 7 million parameter. So the way we set up here was again to not bias our evaluation. During training, we used Llama 7 billion as like a reference policy. So this was fine-tuned by somebody else. I think like the Q LoRa paper had Llama 7B LoRa checkpoint. Okay. That was like trained on helpful and harmless assistant task. We took that as our reference policy. You can fine-tune further. I think it was not a well-trained checkpoint, I think. So we fine-tuned further with just supervised fine-tuning, and we got some amount of bump. If you look at the average reward, you can see it went from 44.7 to 51.9. And all of these like baselines were, we did this on 3 random seeds. So you take 8K conversations, 3 random seeds for each baseline, and then you take the average reward of all 3 runs. You can see that I'm also highlighting average length and average diversity, where the diversity is given as the ratio of unigrams, bigrams, trigrams. So that's how you read this table. So in the first three columns, we have preference-based offline RL methods. Here we found that DPO requires the reference policy to work well. If there is no reference policy, it doesn't work really well. So with the reference policy, surprisingly, the average reward, I was shocked, like it was not actually looking at this external reward model, but still it was able to achieve like a really high score. But when you look at the average, like I was like eyeballing the responses and I saw like a lot of repetitions and it would just, they were like very verbose and it would just go on. It would not know when to stop at a particular token. And like I've confirmed this with other labs and many other people who have experimented with DPO. It just goes on and on and on. It's very verbose. You can like even check their original paper in the supplementary material. They have like some instances. It's very lengthy responses. And subsequently, you can see that the average length blows up. It's like way beyond the test or like the training distribution. So training distribution was like 46, 45 words on average. DPO will go like 66 to even 90, and like different seeds would have very high variance. So you can see like there's like a plus minus 5.9 tokens, and the diversity subsequently drops. If you look at policy gradient methods, here they are only using the good responses, not the bad responses. So it's like already like using half of the data, and then you get like decent performance, like better than SFT. And you would also increase the diversity beyond SFT if you use the reward weighting. But then you switch to ALOL, which is now using advantages, and now you're discarding 33% of the training data as negative advantage. So I like highlighted two of the top responses. Even among the good responses, there was some noise. So if you remove that noise, or like automatically you will have like a positive advantage highlighted with this process. You train on the 67% for one epoch, and actually less than one epoch, and you get like a much nicer performance on the aggregate reward. And specifically like ALOL sec, which was the per token importance weight, that was a shocking result to me. Like it improved the diversity quite a bit. So I was looking at the responses, they were like they came out to be really nice. So this model was really nice tuned. It doesn't go outside the it doesn't have like a length bias as well, like the DPO models have. So it will stay close to the training distribution, and it will like essentially like try to mimic the behavior of the top quality of your data. And this PPO baseline, I was using TRL here. I don't know like if you have used TRL as in your work, but for some reason this was not working really well. So this reference policy was like, you can see like the average length was 51 words. So as I was training with TRL, we had like a much smaller reward model for training. So during training, I used like a 1.4 billion parameter model. And for evaluation, I didn't want to bias it. So I had like a separate test set reward model which was like a 7 billion parameter model. So I think like that 1.4 billion parameter reward model was not really good. So as it did online exploration, it started to focus more on the safety component. And safety component, you had very short rejections as the final response. So you would just say, oh, I don't know, or I'm not gonna answer this or something like that. So we also have like a per component distribution in terms of like, there are like 4 different subsets in helpful and harmless assistant. One is like red teaming part, where you want to be more safe. And other 3 were like, you want to be more helpful towards those who are like Q&A or like opinions kind of questions. So PPO was doing really well on safety, but not on the other 3, because it like kind of like hacked towards biasing towards the safety component too much. So it like yielded very short responses and not that great of a performance. I just to like see that I'm not making a mistake here, I tried an external PPO checkpoint, which was not Llama 7 billion parameter based, but even that one was not very good. It had like the same length bias problem. But overall, like we find that DPO strong preference-based method, but struggles with diversity. And ALOL closes the gap with DPO more or less, but achieves much higher diversity in the final output. And it's also much faster to train actually, since it's only using like a subset of trained. Next, we'll look at the stability of different methods. So first one is preference-based methods. So the blue line here is the reference. You can look at that as like the SFT. So all of the baselines start with the same checkpoint. Your NLL is kind of like in the middle. DPO, like along the 3 runs, it shows like very high variance. So there is no clear signal of when to stop in DPO. It will just like sometimes it will go really high towards the end of the run, sometimes it will go really high towards the beginning of the run. That's actually quite impressive that you just sometimes need like 20% of the training. You don't even need to look at the whole training set to get the best performance from DPO. But there is like a high variance and you don't know where it's going to fall. For policy gradient based methods, you see a much nicer trajectory. So you can see that it gradually saturates towards the top, and there is not like a high variance among 3 random seeds. And advantage stuff, it's like specifically ALOL sec. You would see that it will. So we had like one more trick here. We used prioritized sampling. So instead of just randomly sampling batches from your training set, you can use the reward or the advantage to essentially pick the highest advantage instances first, or like highest advantage instances will be picked more frequently. And if you do that kind of prioritized sampling, you will generalize much faster. Like sometimes you would just need like 50% of the training and you would reach the peak performance. So again, like it seems like you had to like just, there was like a small amount of fine tuning that was needed to get the best juice out of your training data. And I think like many of like recent pre-training methods are kind of showing that high quality training data matters a lot for language model fine tuning. So this was like a nice result that you just need like a small amount of training to get to the high reward regions. Yeah. I guess this is not I like ported this from PowerPoint to Keynote, but effectively what we want to highlight here is that ALOL sec, which is so on the left we are showing GPT-4 safety and helpfulness evaluation. So we do pairwise comparison of model responses with the test good responses. And on the right side, we are doing human evaluations. In both the cases, we saw that GPT-4 and humans both ranked ALOL as more like higher win rate than DPO. So yeah, basically like ALOL is safer and helpful. And yeah, I guess like this concludes our like helpful and harmless assistant task. In the next task, like I said, we have like 5 different rewards. Now here we wanted to like see how robust ALOL is to noise. So we created 2 different subsets of training set. So one is like 88K post comment pairs, which are actually upvoted by humans. And then another 88K pairs which are like exclusively downvoted comments. So like all of these were negatively downvoted, like at least -6 score or lower. Now, if you see like the downvoted versus upvoted distribution across like the 5 classifiers or reward functions that I told you, you can see that the downvoted comments are slightly more unsafe, and they are also likely to be more downvoted according to your classifier. So you can see like bulk of the responses are less than 0.5 probability. So even with like this noisy data, if you apply advantage lol-RL, it will, first of all, it will achieve really high reward on all 5 components. Even though like I aggregated the reward into one single score, it would still get really high performance on everything. So on the top, you are seeing upvoted comments result, and on the bottom, you are seeing downvoted comments result. And naturally, it found more negative advantage data points within the downvoted data. So like 48% of the data was considered as negative advantage. It filtered that. And on the rest, you would do like one epoch or like couple of epochs of fine tuning. And it almost like closes the gap on other other 4 components except for the upward probability. So if you look at like the highest, like the ones that I highlighted in green, ALOL sec. So it's like 93, 93 on fluency, 88, 89 on safety. So even when you start off with more unsafe data, you can still extract safety signal from it, because not all the downvoted comments will be unsafe. And you get like similar on engagement and diversity. Only like the upward probability was not it was not able to match the gap. But overall, like again, like high diversity and consistent results all across. So and then this is like the test set distribution of reference versus the ALOL models. So again, like in each component, you can see that ALOL models like make it like push the distribution up for every reward component in both like upvoted and non-voted comments training sets. And actually, when you look at them side by side, again, like I mentioned, like except for the upward probability, everything else it was pretty close. So ALOL is able to match, like ALOL trained on downvoted comments almost matches the reward distribution on the upvoted comments, except for the upward probability. So overall, like we have the code available. It's like a new offline RL method which can optimize arbitrary numerical rewards on sequence to sequence data. The key assumption here is that we are using like the bandit setting, basically, like the entire output from LM is a single action, and we compute a single value estimate for the entire prompt. It's very efficient. It like discards the suboptimal training data and boosts sample efficiency during training with this prioritized sampling. And we see like really high performance boost compared to FFT and reward based offline RL. Any questions or
Yes, question.
I have a question.
not much. So yeah, I think I'll skip the next. We can just like discuss more if you want to go in more details, and if you want to know more tricks that I found after the paper, we can ask.
So this was a very good presentation. Thanks for presenting. So I wanted to ask more questions about like this is kind of like rejection sampling, right? Like you're rejecting basically the samples based on some indicator, like here it's like a negative advantage function.
Yeah, I mean, I would not call this sampling, more like filtering than sampling, because we are not taking any samples from the trainings, from the language model itself. It's just like plug in arbitrary sequence to sequence data and filter the suboptimal part of it.
Right. So did you like do you have intuitions as to what are the other like good approaches to like filter your data? For example, like I was looking at like this is kind of a problem which exists in like batch RL setting where you have batch, but it's not that prominent because generally in batch RL you have kind of a good data set. But even in those kind of setting, like having like positive advantage and, for example, learning your policy, which is an exponential function of advantage function, like positive advantage function also works well. So is there like some idea of like what could other like extensions be of this, like in terms of like rejecting your data more? Because this is like a problem which highly persists in like LLMs, right? Like you have a good and a bad sample, so you want to figure out ways where you can like remove these bad samples.
I mean, so I have seen like preference-based methods which are emphasizing on making the like good versus bad as distant as possible. So there was like this paper, I forgot the name, but they were trying to contrastively prompt the language model to get like a really bad y negative or like y bad, and then basically your distance between y good and y bad should be more, and like that's like one way to do preference based alignment. But if you are talking about like temporal RL, I am not sure. Like I mean, there was also like this critic regularized regression, or like critic CR or something like that. Yeah, they were they also had like a similar idea for like I think, long, temporal RL problems where they were only looking at the time steps where you had good rewards and just like fine tuning extra on that with offline RL. And you get like a better performance. So I think this has been like explored somewhat in like, temporal stuff as well, but, for language models, I think they are pretty stable, right? The distribution doesn't change. I mean, like, yeah, I think for language models, they are already like very well calibrated, so to speak. So they just need like a small amount of fine tuning. There was like a Lima paper as well. Like if you just do like 1,000 instances of training and you get much better performance from the same language model. So data quality matters a lot for language models, and you also don't want to overfit there. So in our experiments, we just like found one epoch of training is like good enough. It like reaches the top performance very quickly.
Right, so this would lead to like a overfitting problem if you would like overtrain on your, like, for example.
Yeah, I
evaluation
mean, like, if
data.
you just keep training on this objective, I'm guessing that this will like overfit on the top examples, and like there might be catastrophic forgetting at some point, but yeah, I mean, like I was working with a limited budget and I had 2-3 seats as well. So I didn't do like many epochs here, but yeah, I'm guessing that would happen, like if you just keep reusing the same training set again and again.
Hmm. I see.
I have a question about the model that you're using for the filtering. I think imagine that it was initialized from the frozen version of your original model. I wonder
Yeah.
if like the franchise runners, like say if we want to train like Llama will use a less powerful classifier, I wonder if that's going to affect performance.
You mean like, if we unfreeze PyRef and like let it fully fine tune or something?
Or actually to make it even less flexible, like say if you use like say BERT to do the filtering and then
Yeah.
Llama will go to the inside. Wonder if there's an indication of.
I mean, so yeah, I guess, yeah, maybe like that should be like a good baseline, but like the main motivation of why I didn't do that is because you would then have to, for each task, go and define a manual threshold to filter things out. And, I mean, like, since I was like arbitrarily picking rewards, it's not clear, like, how do you set the threshold for TF-IDF, for example? So I didn't do like this data filtering thing. I think for one single component reward, it's more easy to make this choice. But when you have like multi-attribute things, which I'm super interested in, I think this is not very easy to do.
I see, yeah, it does make sense because this is a finance, so you do need the baseline. So.
Yeah. Any other questions?
No. Well, yeah, I don't think there's any other questions. So yeah, thank you so much, Ashutosh, for coming in and presenting today. Really, I think I can speak for everybody. We really enjoyed your presentation. Yeah.
So,